In the winter of 1942, deep inside a roaring American factory, a line of unfinished B-17 bombers stretched farther than the eye could see. Wings the size of small houses hung in heavy steel jigs, their aluminum skin still bare, their ribs exposed like the bones of some giant metal creature. Dozens of workers swarmed around them with drills and rivet guns, each spark a reminder that every second lost here might cost 10 men their lives over Europe. And it was here, in this chaos of noise and pressure, that one riveter would quietly change everything. Not by inventing a new machine or rewriting the engineering drawings, but simply by changing the order in which he put in the rivets. A small decision with enormous consequences, reducing the time to build a wing from 20 hours to just 2. This is the story of how a single pattern, dismissed at first as impossible, reshaped the way B-17 wings were built, and became a symbol of how ordinary workers helped win the most brutal air war in history. At the height of World War II, the Boeing B-17 Flying Fortress was the backbone of the American daylight bombing campaign over Europe. Every bombing raid into German airspace demanded hundreds of these four-engine giants. Every single mission meant tons of bombs, oceans of fuel, and a constant, desperate need for spare parts and replacement aircraft. The United States could not afford to build B-17 slowly. Every delay in the factory meant more bombers missing from the formation, more gaps for German fighters to exploit, and more American crews flying without the safety of numbers. In theory, American industry was ready for this challenge. Assembly lines were running day and night. New factories were appearing almost overnight. Auto workers, furniture makers, and farmhands became aircraft workers. But speed alone wasn't enough. It wasn't just a question of how many people were working. It was about how smartly that work was organized. And hidden inside that vast system was a bottleneck that very few outside the factories ever knew about: the wings. The B-17 wing wasn't just a piece of the aircraft. It was its lifeline. Inside those wings ran the fuel lines, the electrical cables, the control runs that connected the cockpit to the ailerons and flaps. They had to be strong enough to carry heavy bomb loads, plus fuel, plus the stress of flak hits and desperate evasive maneuvers. If a wing failed in flight, the aircraft and its crew were doomed. That strength came from the internal structure and from thousands upon thousands of rivets. Each rivet had to be placed in exactly the right hole, squeezed or driven to the correct shape, and inspected. Every mistake meant extra work. Every delay meant a wing stalled in its jig while fuselages and tail sections piled up behind it. On paper, the existing riveting pattern for the B-17 wing worked. It followed the logical path of the engineers who had designed it. Start at one end, work across the spar lines, then down the ribs, section by section, until the wing skin and internal structure became a seamless, rigid unit. It looked neat, clean, and intuitive on a blueprint. But there was one huge problem. It took almost 20 hours of coordinated work for a team to finish riveting a single wing section, 20 hours for one major component of one airplane. In a war where factories were judged by how many bombers rolled out the gate every day, those hours were deadly. Imagine the B-17 wing assembly bay during the height of the war. Rows of steel fixtures hold half-finished wings at chest level. Compressed air hoses snake across the floor. Men and women in coveralls wear goggles, ear protection, and heavy gloves. Time clocks tick away in the background. Supervisors with clipboards weave between stations, checking progress, comparing reality to the neat charts and production targets pinned on the office wall. Each wing was like a small industrial battle of its own. First, workers would place the pre-drilled skins over the ribs and spars. Then, temporary fasteners would go in. Holes were reamed, burrs cleared. And then, the riveters and buckers moved into position. On one side, a worker holds the rivet gun. On the other, someone presses a heavy bucking bar against the tail of the rivet. The gun chatters, the rivet swells, gripping the metal tight. Now multiply this by thousands. The original pattern for the B-17 wing was essentially linear. Teams would start near the root of the wing and work toward the tip, or from one leading edge section across to the trailing edge, in clean sweeps. On the blueprint, it looked like an orderly march of rivets. In practice, it created chaos. Too many workers needed to stand in the same place at the same time. Riveters bumped elbows, hoses tangled. One pair of workers had to wait while another finished a line because the vibrations and flexing of the metal would distort the holes nearby. Supervisors tried to balance the manpower, but the pattern itself forced a crowd into one narrow zone. The result was a strange contradiction. The factory was full of people, but the wing itself might only have a handful of effective work spots at any given moment. Everyone else waited. And the clock kept ticking. For the engineers, this pattern was familiar. It followed the logical way they thought about structure and stress paths. But the riveters on the floor experienced it differently. They didn't see an abstract diagram. They saw where feet landed, where hands needed to move, where hoses snagged, where a knee had to brace a surface while a partner squeezed the trigger. This difference in perspective, the view from the factory floor versus the view from the drafting table, would soon become the opening for something new, something revolutionary. On that factory floor was a worker who had not started his life as an aircraft specialist. Like many war workers, he came from a totally different world. Years earlier, he had worked in the auto industry, where car bodies moved past teams at a relentless pace. On those assembly lines, there was no room for wasted motion. Every second was studied, every gesture tested for efficiency. In the aircraft factory, his official job title was simple: riveter. He was one of many. But his mind didn't stop at his assigned task. Day after day, shift after shift, he watched not only the rivets he drove, but the entire flow of the wing assembly around him. He noticed how often he had to pause because the bucker behind the panel wasn't in place yet. He noticed how frequently someone had to climb over another worker just to reach their spot. He saw the same problem repeat itself along the entire length of the wing, shift after shift, bomber after bomber. What struck him was not just that it was slow. It was that it didn't have to be. On the auto lines, he had seen something different. Work was broken into patterns that balanced motion, spacing, and timing. The goal was not just to finish a job. It was to finish it in a way that kept everyone moving smoothly, with as few collisions, pauses, and backtracks as possible. In his mind, the B-17 wing wasn't just an airplane component. It was a puzzle of time and movement. And one night, after another long shift surrounded by the constant, deafening rattle of rivet guns, he began sketching. He wasn't sketching new parts or different kinds of rivets. He was sketching a new dance, a new rhythm for the factory floor. He was drawing a pattern. Instead of following the neat, linear order dictated by the drawing, he imagined a pattern that jumped across the wing in a strange, almost chaotic sequence. A rivet line started near the middle, then skipped to the tip, doubled back to the root, and then cut diagonally across the ribs. It looked completely wrong, at least according to traditional logic. But he wasn't thinking like a stress engineer anymore. He was thinking like a man who had stood in those cramped gaps between spars. Who knew exactly how many seconds it took to move from one access panel to another, and who knew where two workers could actually stand without knocking their helmets together. For him, the question was simple: where can people stand and work at the same time without getting in each other's way? Once he had that answer, the rivet sequence almost wrote itself. He was about to challenge more than just a pattern. He was going to tug on a thread of hierarchy, pride, and habit that stretched from the factory floor all the way back to the drawing office. He called it the impossible pattern. When he first showed his idea to a foreman, the reaction was predictable. It looks crazy. The drawing didn't move in straight lines. It didn't follow the spar. It seemed to jump randomly from one surface to another. It violated every expectation of how a wing should be riveted. To an engineer, it seemed to risk uneven stress or unwanted twisting during assembly. The logic that had gone into the original pattern was clear and comfortable. This new approach just looked like a mess. And yet, if someone took the time to trace it slowly, something interesting emerged. Even though the pattern zigzagged across the wing, each rivet still followed the engineering specifications. The spacing remained within limits. The structure was still tied together correctly. There was no violation of the technical rules regarding edge distance or stress flow. What had changed was the order, not the content. By reordering the sequence, the pattern avoided clustering workers in one narrow zone. Instead of having 17 people crowded around a single rib line for hours, it split them across the wing, then rotated them in a choreographed sequence. While one team finished a line near the leading edge, another team worked in a spacious section near the trailing edge, and another up toward the tip. At first glance, the pattern was impossible because it looked like chaos. At second glance, it was precisely the opposite. It was a hidden choreography. The real genius of the idea was that it treated time as an invisible material in the factory, just as real and critical as aluminum or steel. The original pattern had only considered stress and structure. The new pattern considered motion and timing. But to the foremen and engineers, years of habit and authority stood in the way. This was not how things were done. Production was already running at full speed. Who was this individual riveter to tell the designers and planners how to order their work? For a while, the pattern lived only on folded scraps of paper and in whispered conversations around the break tables. Then the war itself made sure it would be tested. By 1943, the air war over Europe had become brutal. B-17 formations flying over Germany faced waves of fighters and walls of flak. Losses were heavy. Each large raid could result in dozens of aircraft failing to return. For the men and women in the factories, these numbers were not abstract. The photos on the bulletin boards, the telegrams arriving in small towns, the radio reports of battles over Schweinfurt, Regensburg, and Berlin made one thing painfully clear. Every additional bomber mattered. When word came down from Washington that production had to increase again, the factory managers had few options left. They couldn't conjure up unlimited new workers. They couldn't magically expand the physical size of the plant overnight. The machines were already running around the clock. They had to find a way to do more with what they had. Somewhere between the pressure of the front and the limits of the factory, that strange riveter's pattern moved from the fringe to the center. A supervisor, perhaps more curious than the rest, decided to allow a small experiment. One wing, one section. One chance to see whether this so-called impossible pattern was a fantasy or a hidden weapon. The conditions were strict. The structure could not be compromised. Inspection standards would remain exactly the same. The only difference allowed was the order in which the rivets were placed. The riveter who had dreamed up the sequence now had to prove that his chaotic-looking path could survive contact with reality. On the day of the test, the atmosphere in the assembly bay felt like a quiet kind of tension. This wasn't a formal ceremony. There were no journalists, no speeches. Just a group of workers, a skeptical foreman, and one wing section hanging in its jig. The factory already knew how long the standard pattern took. Records showed the average time needed to complete a wing assembly following the accepted order. Depending on how experienced the crew was and how many interruptions they faced, the number hovered around 20 hours. 20 hours of people climbing, ducking, waiting, and out of each other's way. The team for the experimental run was briefed. They would follow the riveter's new pattern exactly. No improvising. Positions and rotations were assigned in advance, step by step. Every worker would know not just what to do, but when to move and where to stand next. As the clock started, something immediately felt different. Instead of a crowd swarming one small area, workers spread out along the entire length of the wing. Rivet guns started in several locations at once. Inside the wing, the buckers moved carefully according to the same pattern, ready at each location before the guns started firing. Where the old method had often created traffic jams, this new approach created flow. When one worker finished a cluster of rivets, They didn't stand around waiting for space to open up. They already had their next assignment several feet away, coordinated so that no two people tried to occupy the same narrow gap at once. To the casual eye, the scene still looked busy and noisy. But to anyone watching closely, there was a rhythm to it that had not been there before. The minutes turned into an hour, then the impossible happened. What everyone thought would take 20 hours was finished in just 2. A full 10 times faster. The foreman, who had been skeptical from the start, walked the length of the wing, checking the work. He ran his hand over the rivet lines. They were perfect. The inspectors came next, tapping and measuring, looking for any flaw, any deviation from the standard. They found none. The wing was structurally perfect, built to the highest military specifications. It just happened to have been completed in a fraction of the time. News of the 2-hour wing spread through the factory like wildfire. At first there was disbelief, then excitement. The impossible pattern was suddenly very, very possible. That single experiment triggered a revolution on the assembly line. The new sequence, once just a theory on a scrap of paper, was adopted, refined, and implemented across the entire plant. Production numbers didn't just inch up, they skyrocketed. The factory, which had already been performing miracles, found another gear. B-17s started rolling off the line at a rate that had seemed unimaginable just weeks before. The story of the 2-hour wing is more than just a tale of manufacturing efficiency. It's a powerful lesson in how innovation often comes from the most unexpected places. It wasn't a high-level engineer or a time and motion expert who broke the bottleneck. It was a worker on the floor, someone who understood the physical reality of the job in a way no blueprint could ever capture. He saw the problem not as an engineering puzzle, but as a human one. He saw the workers not as cogs in a machine, but as a team that needed space to move and a rhythm to follow. His genius was in seeing the hidden choreography within the chaos. He transformed a crowded stop-and-go process into a smooth, continuous flow, proving that sometimes the most profound changes come from simply rethinking the order of things. This quiet revolution, born out of necessity and a deep understanding of the work, played a small but vital role in the larger war effort, helping to put more bombers in the sky when they were needed most. It is a testament to the idea that the best solutions are often found by those closest to the problem. Supervisors checked their watches, then glanced at the progress on the wing. They ran their hands over sections that were already done. The quality was perfect. Every rivet was seated correctly. Every fastener was in place. The structure was solid. And still, the strange, flowing pattern of work continued. By the time anyone even thought to check the old 20-hour benchmark, something truly remarkable had happened. The last rivet went in. The air hoses hissed as the line was shut off. The rivet guns fell silent. The wing was done. From a bare framework to a fully riveted assembly. The clock wasn't anywhere near the 20-hour mark. It was closer to 2. Even if you allow for some rounding, some starting and stopping, the raw truth was undeniable. This impossible pattern had done something that no amount of shouting, pressure, or overtime had ever achieved. It had taken the same number of workers, using the same tools on the same wing, and made them 10 times faster, simply by changing the sequence of their movements. The first test didn't just impress the supervisors. It shocked them. Now, in many stories of wartime innovation, this would be the moment where everyone smiles, shakes hands, and immediately adopts the new method. But reality is usually more complicated. Accepting this new pattern meant admitting that the old way had been incredibly inefficient. It meant acknowledging that a frontline worker, not a senior engineer, had found the key. It also meant rewriting instructions, retraining crews, and rethinking schedules that were already carved into charts and manuals. So naturally, there was resistance. Some argued the test was just a fluke. Maybe the crew was unusually motivated that day. Maybe the timekeeping was off. Maybe the wing they chose for the experiment was just an easy one. Others worried about unseen consequences. If the riveting pattern changed, would the wing flex differently during assembly? Could there be long-term structural issues that would only show up after hundreds of hours in the air? So they ran more tests. Different crews were trained on the pattern. Their results were compared. Inspection teams checked and rechecked every finished wing. Engineers revisited the stress diagrams to make absolutely sure that the new sequence didn't introduce any hidden problems, and again, the results were the same. The time savings were real. The structural integrity was perfect. As the evidence piled up, the tone began to change. What had once been dismissed as impossible slowly became a point of pride. Factory managers started talking about the new pattern as a sign that their plant was leading the way in wartime efficiency. The riveter who had drawn those first strange lines on a scrap of paper didn't become a Hollywood star. There were no newsreels dedicated to his face. But inside that factory, people knew who he was. They knew that a man who had once simply tightened bolts on car frames had helped unlock a new way of building bombers. Once the decision was made to adopt the pattern across the factory, a whole new kind of work began. Someone had to translate the riveter as intuitive choreography into instructions that could be understood by every crew on every shift. Charts were redrawn. Instead of clean, straight lines, they now showed a complex network of arrows and numbered clusters. Training sessions were held where teams walked through the pattern step by step, like a dance, before they even touched a real wing. But it wasn't enough to just say, "Drive these rivets in this order." Supervisors had to explain the why behind the sequence. They showed how the pattern prevented workers from getting in each other's way. They demonstrated the rotations between positions so that no one was left idle or overburdened. And they emphasized over and over that the strict quality checks remained exactly the same. Of course, initial confusion was inevitable. For workers used to the old familiar path, the new pattern felt strange, even awkward. Their muscles remembered where to step and how to reach. Their habits pulled their hands toward the traditional starting points. Some grumbled about the change, but then the clock started to speak for itself. On every shift, crews could see the difference in their own time logs. Where they had once spent an entire day wrestling with a single wing, they now saw entire sets of wings moving through the assembly bay faster than ever before. As the new pattern spread, the impact rippled out far beyond just the wing section. Because wings were no longer the bottleneck, the entire assembly schedule could be tightened. Fuselages didn't pile up waiting for their wings. Final assembly lines operated more smoothly. Valuable storage space was freed up. Transport schedules became more predictable. It all began with a single riveter asking a simple question: how can we stand and work without blocking each other? By the time his idea reached full implementation, it was influencing everything from shift planning to shipping logistics. From a distance, this story might sound like a miracle. A tenfold increase in productivity just doesn't happen. But beneath the surface, the success of the impossible pattern rested on a deep understanding of something that is often ignored in technical drawings: human bodies. The original wing assembly pattern was based purely on structural logic. Engineers thought about lines of stress, load paths, and the order in which certain elements needed to be locked down. Their perspective was abstract and mathematical. The riveter's perspective, however, was physical. He thought about which section of the wing a worker could reach without twisting awkwardly. He considered how long it took to crawl inside the structure and move from one access hole to another. He understood the mental fatigue of doing the same repetitive motion in a cramped space for hours on end. Where the old pattern created zones of high congestion, the new one spread workers out. Where the old pattern forced one team to wait for another to finish an entire length of rivets, the new pattern interlaced small clusters of work so that multiple people could move in parallel. In modern terms, he had unconsciously applied principles of ergonomics and operations research. He balanced the workload across the team. He reduced wasted motion. He turned a slow serial process into a fast parallel one without changing the tools or the basic task. What made his idea so powerful wasn't magic. It was a profound respect for the reality of human work. And this is one of the quiet lessons of the story. In wartime factories, workers were sometimes treated as interchangeable units on a chart, measured in headcounts and man-hours. But real productivity often depended on how well those human beings were allowed to move, think, and adapt. The impossible pattern proved that listening to the people who actually held the tools could unlock improvements no expert had ever considered. While this new pattern was transforming life on the factory floor, B-17 crews were continuing to fly into the very heart of German defenses. From bases in England, massive formations took off before dawn, heavy with bombs and fuel. They climbed toward their assembly points, where dozens, sometimes hundreds of bombers would join together into great defensive box formations. Inside those aircraft, young men sat in cramped turrets and narrow waist positions, trusting their lives to the strength of the wings that carried them. Most of those men never knew the name of the riveter who helped build those wings faster. But the connection between the factory and the front line was very real. Every reduction in assembly time meant more bombers were available for operations. More aircraft meant missions could be flown with tighter, more defensible formations. Tighter formations meant more overlapping fields of defensive fire from their machine guns. And that, in turn, increased the chances that crews would survive their dangerous tours of duty. It's impossible to draw a straight line from one riveter's pattern to a specific mission saved. War is far too chaotic for neat calculations like that. But when you imagine a bomber barely making it back over the North Sea riddled with holes in its fuselage and huge chunks of its wing missing, it's not hard to see how every single aircraft built on time mattered deeply. The B-17 became a legendary symbol of American industrial might and air power. Photographs of those dense formations over Europe still fill our history books. Yet behind every one of those aircraft was a factory story, like this one story where ordinary workers found extraordinary ways to push beyond what everyone thought was possible. The story of the impossible rivet pattern is part of a larger truth about World War II. The war wasn't just decided on the front lines or in the skies. It was decided in drafting rooms and laboratories, and also on factory floors where gear teeth were cut, shells were filled, and wings were riveted. Sometimes innovation came from famous engineers whose names we still remember. But other times it came from a riveter whose name appeared only on a payroll sheet. The key thing to understand is that innovation in wartime industry wasn't always about brand new machines or revolutionary materials. It was often about the process, about how to sequence work, how to organize a space, how to harness the instincts and experiences of the people who spent all day with their hands on the product. This was especially true in American wartime production. The United States had immense resources, but it had to learn how to use them efficiently. Techniques from the auto industry, from mass production of consumer goods, were adapted to the massive demands of building military equipment. The riveter's pattern for the B-17 wing is a perfect example of that crossover. He brought the mindset of the car assembly line, where constant flow was king, into the world of aircraft construction, which had historically been slower, more like a craft, and far less optimized. In doing so, he bridged two entirely different industrial cultures. After the war ended, many of the factories that had once turned out bombers returned to civilian production. Workers went home or moved on. Yet the lessons learned during those frantic years didn't disappear. Process improvements like the impossible pattern deeply influenced post-war thinking and manufacturing. The idea that small changes in sequence could generate huge savings in time and labor became a cornerstone of many later production philosophies. Industrial engineers began to systematize what that riveter had done intuitively. They drew value stream maps. They measured cycle times. They studied how to redesign work to reduce bottlenecks and balance tasks. In the language of later decades, they would talk about lean production, just-in-time deliveries, and continuous improvement. But during the war, it was much simpler. They just talked about getting the job done faster without sacrificing quality. For those who care about the history of World War II, stories like this are a powerful reminder that the conflict wasn't only about generals and great battles. It was also about the people on the home front who used their minds as well as their hands. The riveter who dared to say, "What if we did it in this order instead of that one?" didn't carry a rifle or fly a bomber. But he helped ensure that the people who did had the tools they needed to do their job and come home. When we hear the word hero, our minds often go straight to the front line. To bomber pilots guiding damaged aircraft home on 2 engines. To gunners firing at attacking fighters through shattered plexiglass. To infantrymen advancing through mud and fire. And those incredible acts of courage absolutely deserve our deepest respect. But there's another kind of heroism that is quieter and much harder to see. It's the kind that happens when someone takes responsibility for improving the system around them, even when they're just one person in a massive machine. The riveter who developed the impossible pattern didn't have the authority to order anyone around. He didn't command thousands of workers. Yet he took the risk of challenging established practice because he saw a better way. He didn't demand recognition. He just pushed until someone finally listened. His courage wasn't measured in bullets fired or missions flown. It was measured in persistence. And in a war where victory depended on the ability to outproduce the enemy, that kind of courage mattered more than most people realize. So the saga of the impossible rivet pattern for the B-17 wings is more than just a clever anecdote. It's a window into the deeper forces that shaped the outcome of World War II. It shows us that large historical events often turn on small, human-scale decisions. A man staring at a wing jig at the end of a long shift decides that there must be a better way. He sketches a new sequence. He argues for it. He proves it works under pressure. This story also reminds us that technology isn't just about hardware. It's about the processes that bring that hardware into existence. The B-17s that filled the skies over Europe weren't just products of aluminum and engines. They were products of organized human effort, refined and improved by people who rarely get mentioned in the history books. It highlights the critical importance of listening to those closest to the work. The people who stand in the noise and the heat, who feel every awkward stretch and wasted step, often see problems and solutions that distant planners simply cannot. And finally, it offers a hopeful message. Even in times of immense destruction, human creativity can find ways to reduce waste, increase efficiency, and ultimately, save lives. In this case, that creativity allowed more aircraft to be built faster, giving crews a better chance of flying in numbers strong enough to survive and complete their missions. The next time you see a photograph of a B-17 formation, try to look past the dramatic silhouettes and contrails. Think about the invisible pattern of rivets hidden inside each wing. And think about the invisible pattern of decisions that made those wings possible in time. Somewhere in that story, hidden between the aluminum sheets and steel jigs, is the trace of one riveter who refused to accept that things had to be done the way they had always been done. His pattern was called impossible. It just happened to work. Thanks for watching. If you found this story as fascinating as I did, please consider subscribing for more deep dives into the hidden history of technology and innovation. See you next time.